this is our AP Chemistry Chapter 7 lesson video part 1. And in this part, we're going to cover section 7.1 through 7.3. The good news is we already learned periodic trends back in Honors Chem, so hopefully you just need a little bit of a refresher. So if you do need more intense coverage of this, the periodic trends more than I probably have in this PowerPoint, you can go back to my Honors Chemistry Chapter 6 lesson videos. That's when we cover periodic trends in Honors. Alright, so 7.1, development of the periodic table. The periodic nature of the table arises from the repeating patterns in the electron configurations of the elements. Elements in the same column of the table contain the same number of valence electrons. So everything in group 1 has one valence electron. All their electron configurations end in S1. So it's 1s1 or 2s1. Everything in group 2 has two valence electrons, and they all end in ns2. If you skip across transition, because of course we skip transition for valence electrons, everything in group 13, the boron column, has three valence electrons, which makes sense because they all end in s2p1. So there's your third. And it works its way across. We talked about this in the last chapter. So Mendelev's table. Mendeleev created the first periodic table by arranging elements with increasing atomic weight. So he did not know about atomic number yet, and so they were using mass at that point in time. Mendeleev predicted properties of undiscovered elements based on their location on his periodic table. Henry Moseley studied the X-ray frequencies produced when elements were bombarded with high-energy electrons. Each element had a unique frequency which increased as atomic mass increased. From this data, Moseley assigned each element an atomic number, the number of protons. I should say an atomic number. Okay, so once Henry Moseley determined number of protons, atomic number, that's how we arrange our periodic table, is by atomic number instead of by mass, like Mendeleev used. So section 7.2. Wow, 7.1 was fast. Effective nuclear charge. Since electrons are negatively charged, they are attracted to nuclei, because of course a nucleus is positively charged, which are positively charged. Many of the properties of atoms depend on their electron configurations and on how strongly their outer electrons are attracted to the nucleus. So y'all, when we get into the deep part of periodic trends, it's all based on two things: distance from the nucleus and the strength of the nucleus. There's just a third thing that sometimes we talk about, and that'll be electron-electron repulsions. But whenever we are focusing on a periodic trend, and you need to explain something, why something's larger than something else, why does this happen and not this, you need to focus on the strength of the nucleus, the nuclear charge, hence the reason we're about to talk about effective nuclear charge, and the distance from the nucleus. So the force of attraction between an electron and the nucleus is based on Coulomb's law and depends on two amounts. This is what I just told you. The magnitude of the net nuclear charge acting on the electrons. So we're talking the strength of the nucleus. Are there 3 protons or are there 20 protons? 20 protons has a higher net nuclear charge. And then the average distance between the nucleus and the electron. Are the electrons in the first energy level and they're very close to the nucleus, or are they in the 6th energy level and they're far from the nucleus? Those are what determine all of the periodic trends. So, effective nuclear charge. Effective nuclear charge is the actual nuclear charge minus the shielding effect of the core electrons. So Z effective is always less than the actual nuclear charge. So Z effective is the actual nuclear charge. Actual nuclear charge is just atomic number minus the screening constant. That's what we call S, and that's just the number of core electrons. So you are subtracting anything that is not valence electrons. Okay? Now, we don't really need to be able to subtract to determine this number or anything like that, but you just do need to realize that Z effective is going to be a little bit smaller, especially depending on how many core electrons you have. But you need to make sure you know actual nuclear charge is just atomic number. So what's our trends? Well, Z effective trend across. The effective nuclear charge increases as we move across a row or period on the table, although the number of core electrons stays the same as we move across, the actual nuclear charge increases. So as we move across, electrons are being added to the same energy level. So our shielding effect is not really increasing at all. They have the same number of core electrons, but the nucleus is getting stronger. The actual nuclear charge is increasing. Now what happens when you go down? Well, going down a column, the effective nuclear charge increases slightly, So remember, this is our one where it's increase and increase. Actual nuclear charge is increasing as you move down a group, but the larger electron cores are less able to screen the valence electrons. Okay, so as you move down, clearly the nucleus is getting stronger. We have atomic number 1, then 3, then 11. And yes, we are adding more core electrons, but the farther the core electrons are from the nucleus, the less they can screen or shield the valence electrons. So that's why it still does increase slightly. All right, so section 7.3, sizes of atoms and ions. So this is what we'll end with in this video. So bonding atomic radius is measured by halving the distance between the nuclei of the two bonded atoms. So in other words, if I know the radius of a chlorine atom, I can just do that radius plus that radius and get the bond length or the distance between the two. So this is going to use a figure in your book. Now this is the old book, so it may be on a slightly different page, but ours is called figure 7.7 on page 261, and it's just showing you the radius of all the different elements. So the numbers that I'm pulling are just the radii of those elements. So it says use that figure to predict the bond lengths of a CS, a CH, and an SH bond in this molecule of our methyl mercaptan. All right, so I'm just pulling the numbers from that chart. Okay, so I have a CS bond. That means I want to take the radius of C, which is 0.77 angstroms, and add the radius of S, which is 1.0 angstroms. When I add those together, that would give me a bond length of 1.79 angstrom. Okay, because all we're saying is we have C and we have S. Okay, S is a little bit bigger. So if we know this radius for C and we know this radius for S, we can add them together, and that's what we call our bond length. Okay, so that's all we're doing here. Super easy, super simple math. So we have C and H. So again, C is just 0.77 angstroms. I'm just pulling these numbers from this figure. Again, it may just be on a different page in the new book. And then 0.37 angstroms for hydrogen, because of course hydrogen is much smaller. So I get 1.14 angstroms, just like that. All right, and our last one is SH. So S has a radius of 1.02 angstroms, and hydrogen has a radius of 0.37 angstroms. So once I add those together, I get 1.39 angstroms. So like I said, you should have a figure similar to this in your book. It just shows a periodic table and it shows the radius of all the different elements, and that's all I was pulling from. And it happens to be on page 261 in the old book. I don't know what page it's on in the new book. All right, so maybe pause it. Hopefully you can find the chart. Otherwise you can probably just Google the radius. They'll be similar to what's in our book. They might be slightly different. All right, and try this one. So I'll assume you've done that, and let's look at it together. So it says predict which will be greater, the PBr bond length in PBr3 or the ASCL bond length in ASCL3. All right, so we're looking at PBr versus ASCL. Which one is greater? Okay, so I just pull my numbers. So P is 1.06 angstrom, and Br is 1.14 angstroms. So I get a total bond length of 2.2 angstroms. All right, so now I need to check ASCL. So AS is 1.19 angstroms, and CL is 1.99 angstroms. So I get 2.18 angstroms. So who is the greater bond? PBr would be the larger bond, because of course it has the higher number associated with it. Okay, and of course you don't need to memorize any of these radii. Okay, you would need to know the trends, that as you go down, atomic radius increases and across it decreases, but you don't need to know the actual numbers. So here's the trends. So what's the trend going down? Well, within a group, atomic radius increases from top to bottom. So yeah, as you go down, you can see there is an increase. Why does that happen? This trend results primarily from the increase in the size of the energy level. So hydrogen only has one energy level. Lithium has 2, sodium has 3, potassium has 4, so that's why it gets bigger. Those energy levels are farther from the nucleus. So what happens going across? Well, within each period, atomic radius tends to decrease from left to right. So we're adding electrons to the same energy level as we go from left to right. So they're not getting any bigger, but you may wonder, well, then why is it getting smaller? Well, Well, that's because of the nucleus. As we go across, we're adding protons to the nucleus. As the nucleus gets stronger, it can pull the electrons closer. So the major factor influencing this trend is the increase in Z effective. The increase in Z effective draws those valence electrons closer. Okay, so like I said, y'all, the main things to focus on periodic trends are distance from the nucleus, which is related to number of energy levels, and that Z effective, that stronger nucleus. All right, so it says arrange the following atoms in order of increasing atomic size, P, S, A, S, and SE. All right, so on the periodic table, you'll definitely want one of those out. They are arranged like this, P, S, A, S, S, E. All right, so y'all, I always like to focus on one row at a time. So I know that atomic size increases as I go down. We're putting them in order of increasing. So I know that these are going to be the smallest ones. I also know it decreases going across. So who's smaller between P and S? S's. So that's going to be my smallest. Then P would be a little bit bigger. Now I move down to my bottom row. This row is bigger. But between these two, it decreases across. SE is smaller. And then AS is my biggest one. Okay, so that's all you have to do. Is just focus on one row at a time. All right, if you'll do that, it won't be as overwhelming as when you look at a block of 4 of them and are like, oh my gosh, what do I do? Okay, so y'all try this one real quick. You pause the video. I'll assume you've already done that. And then we'll do it together. So it says, arrange the following atoms in order of increasing atomic radius. So we have Na, Be, and Mg. So these are set up like this. We have Be, we have Mg, and we have Na. So in other words, all they left off was lithium in this block. Okay, so remember, I know it increases going down and it decreases going across because they're asking me about radius. So if I want the smallest one first, I want the one that's on the lowest energy level, which would be Be. So Be is going to be the smallest. Then when I go between these, I can see it decreases across. So Mg will be next, followed by sodium being the largest. And see, that's the oddest thing, is to think that sodium is bigger than magnesium, because you want to feel like magnesium should be bigger because you know it has an extra proton and electron. But remember, that extra proton pulls it in and actually makes it smaller. All right, so let's move on and talk about ions real quick. Okay, so we talked about atomic radius, we talked about Z effective. Again, you can go back to my Chapter 6 lesson videos if you need a little bit more intense discussion about it. So cation radii. Cations are smaller than their parent atoms because electrons have been removed from the outer energy level. So the remaining electrons are pulled in even closer by that nucleus. Okay, so think about if you have 10 protons and 10 electrons, but then you take away an electron. Well, now you have more protons than electrons, so that nucleus can pull those electrons in even closer. And then anions are the exact opposite. So anions are larger than their parent atoms because electrons are added, which increases the electron-electron repulsion and causes them to spread out. So the problem is you're adding an electron, but you didn't add any protons. So now all those electrons are all bent out of shape, because remember, they're going to repel one another because they're all negative. So cations lose electrons and get smaller. Anions gain electrons and get larger than the parent atom. So ionic radii increases as we move down a group because, again, even though we're removing and adding electrons, you still gain a new energy level every time you move down on the periodic table. So it says arrange these atoms in order of decreasing size. Oh, this should say atoms and ions because we have some ions in here. All right, so we're looking between magnesium and calcium. So first of all, let's find them on the periodic table. So on the periodic table, we have magnesium up here and we have calcium down here. Okay, so atomic radius increases going down. So does ionic radius. All right, so it says put these in order of decreasing size. You know, that's where you gotta be careful. It's many, many times we ask you for increasing, but every now and then we'll throw you a curveball and ask you decreasing. And you could have gotten it right had you just noticed. All right, so who's smaller between calcium and magnesium? Magnesium is smaller. Well, it doesn't give me magnesium as an atom, so I'll put my magnesium with the 2 positive charges as my smallest. All right, so then calcium is going to be larger, but now I have 2 to pick from. I have calcium and see, and I just totally messed up because I just started doing it increasing size. See how easy it is to mess up for decreasing? All right, so we want the biggest one first. Sorry. So we're not looking at magnesium, we're looking at calcium, but I have calcium and calcium positive 2. Well, I know once I lose electrons, it becomes smaller. So calcium, the atom, is going to be the largest. Then when it loses 2 electrons, that's going to be a little bit smaller. But then because magnesium has 1 less energy level, when it loses 2 electrons, it's going to be the smallest. And so that's what we would do for that. And so see how easy it is to do increasing instead of decreasing? So just be careful of that. That's just one of those unfair things that, people like to do sometimes. All right, so you pause it and you try this one. I'll assume we've done that. So it says, which of the following atoms and ions is the largest? So this time I don't have to put them all in order, although I will do that for y'all. We just have to pick which one's the largest. So first I find S and O on the periodic table to compare them. So if you look, O is right above S on the periodic table. So it says which of the following is the largest. Well, I know it increases going down, so I'm not even focusing on O. I'm focusing on S. So is S or S negative 2 the largest? Well, remember, once it gains electrons, it becomes even larger. An anion is larger than the parent atom. So S negative 2 would be the largest. But if you were going to put them all in order of increasing, oxygen would be the lowest because it has 1 less energy level. Then sulfur, the neutral atom, and then sulfur with the negative 2 charge. That would be order of increasing down here. All right, so hopefully you got that one right. All right, so an isoelectronic series is a group of ions all containing the same number of electrons. In an isoelectronic series, we can list the members in order of increasing atomic number, and the radius will decrease. Okay, so if you look, oxygen starts out with 8 electrons, but it has negative 2, so it has 10 now. Fluorine starts out with 9 electrons, but it has a negative 1, so it has 10 now. Oh no, I feel like the coughing's coming on again. Gosh. Sodium has 11 electrons, but it has positive 1, so now it has 10. So forth and so on. I clearly can't continue giving you the example. Hang on, let me get some water. Oh my gosh. Alright, so all of these end up having 10 electrons. I'm not going to explain the last two because clearly I'm just trying to make it through the video at this point. Alright, so if I put them in order of increasing atomic number, so see it's 8, 9, 11, 12, 13, it's in decreasing atomic radius. Because the oxygen's getting much bigger because it's gained 2. Fluorine's only getting a little bit bigger because it's gained 1. Sodium has lost 1, so now it's getting a little bit smaller. Magnesium's lost 2, so it's getting even smaller. And aluminum's lost 3, so it's getting even smaller. So see, we go from getting bigger to getting smaller and more small as we go across. All right, so if you ever need to do an isoelectronic series and you want decreasing atomic radius, just put them in order of increasing atomic number. And to see, here's all of them, but this one also includes Ne in its neutral form because it has 10 electrons. All right, so let's look at the sample exercise and hope that I can just, make it through the rest of this video. I think we're almost at the end. All right, so it says arrange the ions in order of decreasing size. So I can see that K normally has 19, but it's positive 1, so that's 18. Cl normally has 17, but it's negative 1, that's 18. So they all have 18. So I can say, hey, this is an isoelectronic series. We want them in order of decreasing size, so I put them in order of increasing atomic number. So out of K, Cl, Ca, and S, who has the lowest atomic number? It's S. So I put S first. Next is Cl. So I put that next. Next is K. So I put that next. And last is Ca positive 2. So see, I put them in order of increasing atomic number, and so that puts it in order of decreasing size or radius. Okay, so that's all I have to do. And so you just have to look at them to make sure it is isoelectronic. Just make sure they have all the same number of electrons. All right, so pause it, try this one, and then I'll assume you've done that. So it says, which of the following ions is the largest? So you didn't even have to put them in order. Okay, well I can see Rb starts with 37, but it's lost 1, so it's 36. Sr starts with 38, but it's lost 2, it's 36. Y starts with 39, it's lost 3, so it's 36. All right, so if I want the largest, I want the smallest atomic number. So if I look, that's going to be Rb positive. Okay, so the smallest atomic number is going to give me the largest ion. All right, so hopefully you got that one right. All right, and then that's it for today, thank goodness, because I don't think my throat's going to make it through this because I stopped to teach fourth period. Well, hopefully you're kind of jogging your memory about some of these periodic trends, and so we'll continue in our next video.